Greetings and welcome. In this session, you will be able to explain hydrostatic law. Hydrostatic law, it states that pressure intensity at a point in a stationary fluid varies directly as the depth of the point below the free surface of the liquid. Here, this is the practical real life example. Here you see this is the dam that is called as reservoir. The huge amount of water is stored by the construction of wall across the river. This water is stationary. So here by the water the pressure is developed. This pressure is acting on this wall, also on the ground surface. So this acts in equal in a magnitude in all direction, that is as per the Pascal's law. But vertically this pressure varies as the height from the free liquid surface is increasing. That is what we are going to see. Now here, as per the common observations, pressure at free liquid surface means this is a top surface. Now this is a gauge pressure, that is 0. So here also in this image or clip we see this is a dam and this is the water top surface. So pressure acting or pressure at this free liquid surface is 0. That is gauge pressure. Absolute pressure is atmospheric pressure. Now here this is demonstration. By this you can understand. Here we see this is the water filled with water and it is punctured at various locations. So the water is falling. We see that the rate of falling of water at the bottom hole is higher. Its speed also we find higher as compared to the water which is coming at the upper holes. Means as the depth of this water is more, the rate of falling or speed is more of water. This is because of pressure which is present here is high. So by this demonstration we say that pressure is high at the lower altitude or as the depth of water increases. Now mathematically this we have to prove. So that is what derivation that we will see of the hydrostatic law. So this is the statement. It states that the rate of increase of pressure in the vertical direction, means downward direction, at a point in a static fluid is equal to the specific weight of the fluid. For the derivation we need to have diagram. So this is a small fluid element which is taken. It has two surfaces, upper surface ABCD, bottom surface PQRS. Thickness or height of this fluid element is dH, small dh. This fluid element is taken at a depth of small h from the free liquid surface. So as per the definition, pressure is equal to force upon area. So force is equal to pressure into area. Now here some parameters or dimensions you say. This is a fluid element which is smaller. That's why this shaded portion ABCD, that is a cross-sectional area of the element dA and height of element dH. Distance of fluid element from free liquid surface, that is h. Now on this element different forces are acting. These are shown over here. On the AB plane the force is acting. By the definition it is a product of pressure into area. So it is P into corresponding area. This small elemental area means dA. So this force is PdA is acting vertically downward. at the bottom plane PQ, the force is acting, that will be what? P plus delta P by delta H into dH. This is pressure intensity into area dA. And the third force, that is self weight of the fluid element W, acting in downward direction. Now, as specific weight is ratio of weight to volume, so weight is equal to specific weight into volume. Specific weight is a product of density into acceleration due to gravity, means rho into g. And volume of the fluid element is what? This surface area dA into height dH. So here this dA into dH is the volume. Now under equilibrium conditions, all the forces in vertical direction, means sigma Fy, is equal to 0. Sign conventions will use force directing upward taken as positive, and forces acting downward are taken as negative. Now as for this diagram, these two forces are acting in downward direction, so we'll have negative sign, and this force will be having positive sign. So see here, this minus PdA vertically downward, this rho g dA dH, that is weight, vertically downward, and this is vertically upward force plus. Now all these expression parameters, we find dA common everywhere, so it can be cancelled. Also we find here this minus PdA, and here is a plus PdA, so this will be also cancelled. So here what remains, that is delta P by delta H is equal to rho g. So further, this delta P is equal to rho g delta H. This is what differentiation form. Take integration of both sides. Integration of delta P is a P, means pressure. Integration of rho g delta H, in that rho density, g acceleration due to gravity. These are constants, will out of the integration, and integration of delta H is H. So P is equal to rho g H. So rho into g is a gamma, means specific weight. So pressure is equal to gamma into H. Now in this case here, at this step, delta P by delta H is equal to rho g, means gamma. It shows that the rate of increase of pressure, this is the rate delta P by delta H, that is what rate of increase of pressure in a vertical direction, is equal to gamma, means specific weight of the fluid element. And also it gives finally formula of pressure, that is rho g H or gamma H. In this diagram, this is demonstrated that as per the height, as the height from the free liquid surface is increasing in downward direction from the free liquid surface, this pressure intensity is increasing. This is shown by this triangle. So this triangle has number of lines, you see. As the liquid depth increases, this rho gh value increases, means pressure intensity increases. So at the end of this session, you can explain what is hydrostatic law. Subscribe the channel for further video sessions. Thank you.